I was helping a friend teach a class at Berkeley. That was in 2011 and 2012. Then just a couple of years later, they came to me and said, hey, we've got this idea for a Bitcoin ASIC. TSMC is starting fabs in Arizona, Samsung starting fabs in Texas, Intel starting fabs in Ohio. There's actually a lot of commonality between what an AI chip looks like and what a Bitcoin chip looks like. I'm really appreciative of Jihan, and he's very much a long-term strategy type of guy. He's the one that really is pushing for these new advanced technologies. I don't think we've seen anything close to the limit yet.
This podcast is entertainment, not financial, tax, or legal advice. Views expressed represent statements of the speaker in their individual capacity, do not represent the views of Unchained, and should not be considered investment advice. Speakers often have personal, family, or business connections to Unchained, which may include direct financial benefits. Please see our disclosure at unchained.com/podcast.
Hey, everybody. Welcome back to the Bitcoin Frontier podcast. This week I have on Haris Basit. Haris, welcome.
Hey, thank you, Joe. Great to be here.
Yeah, absolutely. Glad to have you. For the audience that may not know who you are, what's your background and how did you get into the semiconductor world?
Okay. So, right now I'm the Chief Strategy Officer for Bitdeer, which is a Bitcoin mining company, global Bitcoin mining company, one of the largest and I think one of the best. And semiconductors, I got into that in sort of a weird way. I wanted to be a physicist, but I figured I wasn't smart enough. So I went into semiconductor physics, which it turned out I liked, and went to a really good school, at least in semiconductor physics space at University of Illinois. And so that got me into that space. Had a really good career there, worked on some great projects, including gallium arsenide that now is in everybody's cell phone. I worked on ultra bright LEDs, which now used in everything from traffic lights to brake lights. And I worked on these things before they were production, right? And in the R&D of them, I did some work on very, very low noise timing circuits that allow us to communicate at very high speeds now, because you need to be able to have very precise timing to be able to do that. And then I also started a company in 2014 with some friends of mine that developed a Bitcoin architecture for an ASIC. And that architecture is pretty much the same one that everyone uses today, several years later. So, but a lot of really interesting experiences within the semiconductor space. Been pretty lucky to work with some very, very sharp people, and had a chance to contribute in several different areas. So, it's been good for me. And I think Bitcoin lends itself to some more creativity in semiconductor design than other types of circuits do.
Interesting. Yeah, I want to dive into a lot of those different topics. Can you kind of at a high level explain what semiconductor physics even is to someone that may be completely out of, not even paying attention to what you're doing?
Okay, so semiconductor physics is just simply the physics of how a transistor works, right? And but mostly it's about that and how to get the material science, and the transistors are really operating using quantum effects, and how those interact and how you can improve that. So, I've left the semiconductor physics world behind after gallium arsenide, really working more on circuits and things like that after that. So, it's a very big field. It's rapidly growing, especially now with AI driving a lot of it. So it's a big area. It's a very interesting area. It requires very highly skilled people. And part of my journey in Bitcoin, especially for circuits, is to use more and more highly skilled folks to do very specialized designs that reduce the number of people who are capable of doing it, right? So that you get benefits that not everybody can get. Because if you do it the standard way, if you just go and say, well, I'm going to get, the same TSMC manufacturing process and use their libraries, then you're going to end up with a result that's fairly similar to what everyone else is getting, because all your building blocks are the same, and there's limits on your creativity. But if you can put in a lot of extra design effort, a lot of extra skill, and go down to the transistor and the wire level and not use the building blocks that TSMC gives you, then you can get a lot more out of it. But it's a lot more effort, a lot more risk, things like that.
How many, do you have any idea of how many people in the world have that skill of being able to really be able to create these semiconductors at a very low level, like instead of using TSMC's libraries like you're talking about?
People who design analog do that all the time. But then to do a digital chip like this using sort of effectively analog techniques, it's a lot fewer than can do it using the libraries. Maybe it's only 10% or less of the number of people that can design using the library, probably even less than that. So it's a reduced set. There's sort of a pyramid or a hierarchy here, right? The number of people that are able to program, just a normal PC to mine Bitcoin is huge. The protocol is pretty easy, and in fact, you can just go out there and find the code. The number of people that then, as it went from software on a PC to GPUs, it's a little harder to program the GPUs, but not much. And that universe of people is smaller. And then it's programming an FPGA. That's a smaller group of people. Then it's designing an ASIC using TSMC's building blocks, which is significantly smaller. And then it's using analog techniques, which is smaller still. So you're continue to narrow down the number of people who can do it and can do it well. It's one thing just to be able to do it. You have to get it to work well. It's a difficult task, and it takes a lot of experience. It's sort of an interesting thing when you get down to, if you go to a company that has a lot of software people and AI, those people are typically in their 20s. Then if you go to a people that's doing digital design, they'll be older. But if you go to a place that is using full custom analog techniques, you really want the gray-haired people, because that experience, it really requires real-world experience, and it's hard to get that just coming out of school. So I've done that in the past. I've hired plenty of people right out of their PhD programs that have been great, but you need a few years to really get good at it.
Interesting. Yeah. So you said you started a company in 2014 that had to do with developing Bitcoin ASICs. How did you get into that space from just doing other work in the semiconductor industry?
So I was helping a friend teach a class at Berkeley, an entrepreneurship class, and I was mentoring some of the students there. And that was in 2011 and 2012. And then just a couple of years later, they came to me and said, hey, we've got this idea for a Bitcoin ASIC. I only had a glancing idea of what Bitcoin was back then in 2014. So I studied up on it, figured out that their approach was could be improved by adding some of the stuff that I'd actually learned helping to design semiconductor chips for military applications. And that some of those techniques and some new techniques that we developed could be used to greatly improve the performance of this type of chip.
Did you recognize it, or I guess how different is the Bitcoin ASIC industry from other semiconductor chips? In my mind, at least, if you create a very efficient Bitcoin ASIC, you now have the ability to just effectively print money at a cost cheaper than everybody else. Is that very different from being able to develop another chip?
There are several differences, right? One thing is most chips that have a lot of value in the digital space are also very large, with hundreds of millions or even billions of components or transistors, but certainly transistors, many more than that. And so you need to use automated techniques and standard cells provided to you by otherwise there's so much design effort that goes into it that it would take you years to develop that chip, to do it, and transistor by transistor, wire by wire. It's just not a practical task. And you can get very big Bitcoin chips too, but if you look at them and a little more closely, you find that they're really much, much smaller blocks that are repeated hundreds of times on that chip, or even thousands of times on that chip. And so you can put the design effort into one of those blocks and then just cut and paste it across the chip. It's a little more complicated than that, of course, but that allows you to use much more intensive design techniques to do it than you can for a normal chip. And the other thing about a Bitcoin chip that's different than a regular chip is that it's pretty much on and operating at full power all the time. Whereas most digital chips, they've got a lot of idle time where they're waiting for, not most, but many, certainly the things that you might think of like a CPU. have a lot of idle time where they're waiting for data or they're waiting for something here or there. They're not really running full blast all the time. Now, that different GPUs, like what come out of NVIDIA, can be running full blast all the time when they're running, especially things like AI or some graphic applications. And so there's actually a lot of commonality between what an AI chip looks like and what a Bitcoin chip looks like. Both can tolerate a fair amount of error. Now, they don't really allow that in graphic chips because sometimes they're doing numerical calculations that don't allow it. But if you're truly doing AI, it's okay to make a mistake now and then. They really won't affect the final result. Same thing in Bitcoin. And there are also smaller circuits that are replicated many times across the chip and leverage the sort of a parallel nature of it.
Fascinating. Can you kind of dive deeper into like what your specific role is at Bitdeer and what you're doing?
Yeah, so as the chief strategy officer, I have 2 or 3 roles. One is this advanced technology development, just to look at how to get the next generation of Bitcoin chips out, what it would take to do that. And so, we announced that we've ordered wafers from TSMC, and we are working on both the existing architecture that everyone uses, but also developing new architectures for the future. And then also, I have responsibilities in basically investor relations and capital markets and things like that. Two very distinct things, but seems to work well.
I'm curious to learn more about the process of like ordering wafers from TSMC. Can you kind of explain that in more detail? Like, what's that look like?
I mean, there's the initial order, right? You make a design, and the design is, of course, on a computer. And that design is then, you have to make a mask from that design. The mask is a physical implementation of the pattern, right? And that's used in the lithography tools. These lithography tools are super expensive, right? They're made by a Dutch company called ASML. I think it costs over $100 million each. And that's what prints these patterns that you've designed on your computer onto the wafer. So the masks themselves can cost many millions of dollars, depending on which node you're using. But they're use them over and over again on thousands and thousands of wafers. So you order the mask, you pay for that. You get a few wafers first, see if they work. And if they do, then you order a lot more later, or as many as TSMC will allow. And it's right now everyone uses these 12-inch wafers, which have been in use for quite some time. I'm not sure what else to say about that.
Our wafers, I guess, like, is that the actual like 12-inch green chip that you see within a Bitcoin ASIC?
Yeah, so that wafer is then diced up into much smaller pieces, right? Pieces that are maybe half an inch on a side. And then those are typically packaged inside of a plastic or ceramic package that connects the chip to a board and to the rest of this. Yeah. So when you look at a mining thing, even if you take the cover off, you'll see the chips, but not really the silicon. You'll see the packaged chips. And so you'll see a plastic or ceramic cover with a bunch of leads coming out of it.
Gotcha. And like currently is TSMC, is that the only company that can really create wafers? Or like how many, people or companies around the world are able to create wafers that you guys or other people design?
So, I mean, the number of people that have wafer fabs is probably in the hundreds or at least many dozens. But the number of companies that can create leading edge processes is very few. So, I mean, right now, TSMC, Intel, and Samsung are the only 3 that are going to the smallest nodes. A lot of other companies have fabs, but they are not pushing down to that very small node size.
In this frontier moment, Haris is talking about where semiconductor chip fabs are all around the world. Here, if you're watching this on video, you can see a global map of semiconductor fabs, which are the facilities where devices like integrated circuits are manufactured. Like Haris mentioned, there are a few dozen major fabs, and they are located mainly in Taiwan, Europe, and the United States. In the context of Bitcoin, it's important that the Bitcoin stack has no single point of failure or potential point of capture. Over time, it would be ideal if more chip fabs were built in different parts of the world, and it would be great if it was more accessible and less capital intensive to build them. With that said, if all major chip fabs did get captured, You still need to manufacture millions of machines and plug them into gigawatts worth of energy. At that point, you'd probably just start mining Bitcoin profitably. In the worst case scenario, a majority of miners can only censor transactions. Economic node runners are the individuals that enforce the rules of Bitcoin, not miners. And now back to Haris.
They are staying at other nodes, especially if they're doing analog or power devices or something that doesn't require very high density, very small transistors.
When you say nodes, is that kind of referring to, I've heard people in the space refer to like 8 nanometers, 6 nanometers. That's okay.
That's it. It's a process node. The shortcut is to say node, but yeah, it's a process node. And it's typically, in the past, it was always defined by a geometric size. And they continued that, but really that geometric size is not meaningful anymore. It's just a way of specifying that, we're going to the next generation. But there's often nothing on the chip itself that's as small as or the size of whatever the node is.
Interesting.
It used to represent the size of the gate that controlled the flow of current. So, if you go back far enough, it was the size of the gate, 65 nanometer or whatever. But now, when we are in the 3-2 nanometer sizes, 3 and 4, it's not really the gate size, but it's a way of saying, hey, this is quite a bit smaller than the previous one because I gave it a smaller number.
Interesting. So you guys design the chips, you send it to TSMC, and then they create the wafer. And so effectively, you guys eventually will receive the chip, or you guys already have received chips, and you would compete. Are you guys competing with Bitmain in that sense?
We will be once we start making this and the others like Canaan and MicroBT. But, one difference is that we will consume a significant amount of these ourselves.
Very interesting. I'm curious, what's the timeline for you guys to, receive the chips, right? Have you submitted the designs already, and what's the progress there?
Yeah. So, we haven't released the timelines exactly, but we expect product, to be out this year, meaning the mining rigs and stuff. But exactly when, we'll find out soon. The chip design is, can be iterative. So it might be that we have to make a few changes to our first design, and that could change the timing or the delay of when we announce our product. But we haven't made any announcements yet on product.
Yeah, how easy, I guess, is it to design a chip and then simulate that chip virtually? And then how much more do you learn from designing that chip, having it created, and then running it and learning more? What's the difference, or how much can you learn?
So it depends how you've done the simulation, right? So a straightforward digital simulation can be extraordinarily accurate in that it shows you that functionally the chip is doing what it's supposed to do. But that's not enough, right? You needed to do that overall variety of statistical changes, like just temperature changes, right? That's one thing. And then there's a lot of process variability, because what you're making is so small that the variability of it can be very large. You can imagine if I'm making something that's a foot in length, just things that people are more aware of, I can make it very, very accurate to very close to being a foot, right? But if I start making it just a millimeter or something that the thickness of my fingernail, it's much harder for me to, on a percentage basis, control that thickness, right? So as things get smaller and smaller, the percentage variability goes up. And now you have to say, well, how well will this chip perform, over all the variation that I'm going to see on a single wafer and across thousands of wafers, and also with the temperature variation, process variation, temperature variation. You have to take those into account, and that helps determine what your yield is going to be. And the other thing that we deal with is something that's a purely quantum effect, which is leakage current or tunneling, so that the gate is off, meaning that there should be no current at all, but there's still some leakage current, and that's because you've got such a small distance that the electrons have to transition through, that even if the barrier is too high in a classical sense for the electrons to get through, in a quantum sense, they'll tunnel through that very thin barrier, and that gives you leakage current. And as it gets smaller and smaller, your leakage current goes up. Also, it goes up exponentially with temperature. So that's a long way of saying that finding out what the yield's going to be, how it's going to operate at temperature, and over process variations, that takes a lot of simulation. So it's not just simulating it once, you simulate it thousands and thousands of times, introducing variation and see what you expect the yield to be, see what you expect the performance to be. And if you do that well, then, it's highly predictive. But then, it's a very difficult, complicated task. There's hundreds of places where you can introduce an error or a problem. So not everyone gets it right first time.
Fascinating. Yeah, I do want to dive deeper into, Bitcoin ASICs. But first, I kind of want to hear more about Bitdeer. I know like Jihan Wu, I believe, is the founder and now he's the CEO. How do you think about him and his leadership at Bitdeer and the rest of the team?
Yeah, so I joined recently. I joined about a year ago. And part of the reason I was willing to join and wanted to join is because of Jihan and the team. I've been in high tech and sort of leading new changes in the technology space in a few areas over most of my career. And I really liked that. I wanted to continue it. And most Bitcoin mining companies really have nothing to do with technology. They're buying warehouses or building simple buildings and putting a ton of these servers that they buy from third parties into them and turning them on. Now that's an oversimplification. There is some technical aspects to it, but it's not anything close to rocket science, right? It's a business that can be in the long term very low margin. It's one of the few things that you and I can do it at home. We can buy a mining rig, the exact same ones that they buy, plug them in, and now we can't scale it. Maybe we can't get the same electrical cost they can, but that is a way of just demonstrating, hey, this is not rocket science. It's something any average Joe can do at home. And so over time, these large Bitcoin mining companies, if they don't have a strategic advantage, if they don't have what we're doing is trying to inject technology as our strategic advantage and say, we're going to have, we already have the lowest operational costs in terms of that, but also have the lowest capital costs if we're making our own machines. And these machines will, over time, become the most efficient machine out there. Then that's our way of having a strategic advantage. That is a moat around the company's business model that is supported by all the effort and IP that we put into developing this high technology. Whereas, a typical business model for a large Bitcoin miner is basically to raise a lot of money out of the capital markets and then transfer it to one of the manufacturers of Bitcoin mining rigs so that they can buy a bunch of rigs. And that's good now, maybe, but it's not sustainable long term. So I'm really appreciative of Jihan.
With tax day on April 15th, high net worth Bitcoin holders could be leaving a lot of money on the table if they don't have a sound financial plan and tax strategy. Sound Advisory is a leading financial advisory firm for long-term Bitcoin holders like yourself. They can help you maximize your Bitcoin wealth while navigating the complexities of the legacy financial system. Don't get killed on taxes. Check out Sound Advisory at thesoundadvisory.com for more information. That's thesoundadvisory.com. Now back to the show.
And he's very much a long-term strategy type of guy. He's the one that really is pushing for these new advanced technologies. And so I think that's a big part of it. Actually, Matt, our current CEO, and at least for the next several days until he takes over the mining business in a much more active way, is also very much into technology. I mean, he's got a technology background, one of the key developers of WeChat, if you know, the largest app out there. So this is definitely the kind of company that I think is right for me. I think it's got a very strong strategic position and based on technology, which is really where I like to play. And I think where Jihan and Matt also like to be. I think that all came together for me, and that was compelling. And I'm happy I joined. It's not been a year yet. I think it's been like 8 months or something like that, 8 or 9 months. But so far, things are working out pretty well.
Awesome. Yeah, you talked about being able to potentially create one of the most efficient ASICs out there. How do you think the Bitcoin mining technology or ASICs will evolve over the coming decades? And like, what do you think that you'll be able to produce that Bitmain or micro BT has not been able to produce?
So the idea is to develop a new architecture, new circuit techniques that can dramatically improve that. We're not prepared yet to say, what we think that might be. We're still in the early stages of that. But we've got some very promising approaches that we're looking at. And so, the goal isn't to be the number 2 or the number 3. The goal is to be the clear market leader, the technology leader. And that's our goal.
Do you have any idea of like how much more efficient you can create a machine just based off designing it in a different format?
I think there's a lot that you can do. A lot. I think you can make tremendous strides.
No, care to expand anymore, or is it mainly a top secret?
I don't want to give a number right now because it's early. We haven't confirmed those numbers very well, and the engineer in me says don't say anything until you've done more validation and verification of it and can show that it's there. As I said, that it's not enough to just say you've got a simulation that works and shows you a particular efficiency. You actually need to demonstrate it to yourself over a wide variety of statistical variations for process and temperature. And, then make sure that you can yield it at a high rate. Otherwise, it's going to be too expensive to make. And then you can say, yes, this efficiency is real. And we're in the process of looking at all of those.
So I guess you would be one, I don't know if you've heard the term that some people throw around, but like the idea of ASIC commoditization, where like you kind of look back over the years at the efficiency of Bitcoin mining machines, like CPUs were super inefficient, then GPUs got a lot more efficient. And like the growth in energy efficiency, I guess, was like decelerating over time, just as ASICs kind of became more of the same thing. You would say that there's still significant growth in efficiency over time. Like, do you ever see that beginning to really plateau, or do you think maybe we've plateaued over the last few years or so, but maybe we'll see additional spurts of growth in efficiency?
I wouldn't be here and working on this if I didn't think we could dramatically improve what the state of the art is today.
And even like say it gets 10 or 10x better or 5x better, is that going to be the limit for how efficient you can design an ASIC, or are there going to be like other avenues at which you can create a more efficient ASIC? Or is it like design, size of chip, that's really it? It's going to be like hard to create something even better after that.
So, I don't know what comes after what we're looking at today, but I think I would be silly to think that there isn't something that comes after it, right? It might be somebody who's much more creative than I am or my team, but, we're doing something for the next generation, and then we have to keep on going after that, right? The team doesn't disband after that. They stay in place and they keep trying to improve it. Now, it may be a big step and then incremental improvements, but, the goal is to really do as much as we can. And, I don't think we've seen anything close to the limit yet.
In this frontier moment, Haris is suggesting we haven't seen anything close to the limit of Bitcoin ASIC efficiency. This is quite interesting considering the growth rate in Bitcoin ASIC efficiency has dropped considerably over time. Here, if you're watching this on video, you can see the diminishing growth in Bitcoin's mining difficulty, implying that the machines used to mine Bitcoin are not seeing massive advancements or breakthroughs in how efficiently they can convert energy into hashes. Over the last few years, I've personally believed that the trend of slowing growth will continue, but Haris seems to suggest that a potential breakthrough is on the way. Time will tell if he and his team have created something that will truly disrupt the Bitcoin mining industry and make a lot of machines obsolete relatively quickly. And now back to Haris.
From your perspective, if you or even someone else is able to create a new Bitcoin ASIC that is 5x more efficient or whatever it is, significantly more efficient than modern ASICs are today, how do you think that would change the Bitcoin mining industry or even Bitcoin as a whole? Or do you have a perspective?
So I don't think it would change Bitcoin as a whole. I think the Bitcoin mining, one thing it would do is that if you sold enough of these, the older machines, the hash rate would grow dramatically, right? So you can think of it this way, right? It's very hard to grow total megawatts in use. It takes time. Sometimes you have to get bulldozers out there. You have to buy transformers. It's not something like you can flip a software switch and do that. So that takes time. So let's call that fixed. It's not really fixed. But it's slower growing than the other things, right? And then, so we'll fix that at some, whatever it is, I don't know, 20 gigawatts or whatever the global hash rate network uses now. And it'll grow, but it'll grow at some slow rate. And then what can grow much faster is the ASICs that you buy supplement, right? And because that's limited by TSMC and Samsung and Intel and anyone else that is, fabricating these things, their wafer capacity. And they have a lot more capacity than they don't want to dedicate that much of it to Bitcoin right now, but potentially that capacity is there. So that could grow much faster. And if it grows and you have more efficient chips, then the hash rate goes way up. And what that means is that the older machines, their profitability declines dramatically, or they don't become profitable at all, and then they have to come offline. So you just get a lot more hash rate with the same amount of power, to zeroth order estimates, right? And you haven't decreased the power, right? Because if people sort of have that power fixed, they've got 100 megawatts and they get a more efficient machine, they're not going to reduce the power so that they can still have the same exahash. They'll use the same power and load it up with the new machines. And so their exahash goes up, power stays about. So I think what that does is it drives the older machines out of business, and the hash rate goes up. And that's why I'm saying this is a Bitcoin mining can be, if you're just in it for buying machines and putting them in there, it's a treadmill. And unless the management's adding some strategic value, figuring out how to make their company have some benefit beyond just buying machines and installing them in mass volume, it's going to be difficult on their profit margins over the long term.
Will there ever be, like you mentioned earlier, how there's like mainly 3 different companies that are able to produce Bitcoin ASICs, like the chip fabs. Will it ever be more accessible to build a chip fab that it can produce top of the line Bitcoin ASICs, or will that always be something dominated by Intel, AMD, and TSMC?
Well, I can't say always, but I don't see an easy path, or really any path, that doesn't require a very large player like those 3. Now, there are other people that can get into that business. I mean, there are plenty of very big companies. If Apple wanted to really get into the semiconductor business, I'm sure they could, and others as well. And maybe at some point they'll think that's strategic and they'll do it. Sam Altman is talking about starting his own semiconductor fabrication thing, though I think he's now saying that the 7 trillion number was falsely reported. But anyway, so it's possible. And I think as the value of semiconductor technology increases, there are some large players that will get into that. I'm sure the Chinese will try to make sure they have a player in the leading edge. I'm sure they're trying that now, and they just don't have the advantage of having some of the ecosystem available to them. Like, for example, the ASML photolithography tools out of Europe are not available to them. But, it's not going to be just 3. But it'll take very large organizations with a pretty good history of this. And it's just really, really hard to make billions and billions of transistors that are very precise in a reliable way. That's probably one of the hardest manufacturing things that mankind has ever done.
Yeah, it's quite fascinating. I guess, what are the biggest hurdles? Is it like financing, like getting the capital to do it? Is it getting the human capital that is able to build, like intelligent people to build these plants? Or is it like just getting the physical machinery that's needed to create these chips? Like, or is it all of the above?
So, I think it's a little bit all of the above. The capital is, for a long time, semiconductor technology wasn't considered very profitable, and the big companies got out of it. A lot of companies that had fabs, take AMD as an example. AMD had a fab. They thought the fab wasn't very profitable. They really thought the design was much more profitable. And so they sold the fab, and that's now Global Foundries. And it turns out they were right. The design was much more profitable than the fab. But that's changing. And I heard one of the founding CTOs of TSMC basically say, it's not so much that TSMC won the semiconductor race as the other companies decided it wasn't worth playing. It's only in the last few years that the semiconductor technology has become as profitable as it has. And now, and also of strategic importance. And so, the government put $52 billion into the CHIPS Act, the U.S. government, and then other governments have put in money too. And the industry has really responded. There's hundreds of billions of dollars in response from, the industry. TSMC is starting fabs in Arizona, Samsung starting fabs in Texas, Intel starting fabs in Ohio, and I think Micron is starting this huge fab in New York State. So that 52 billion has actually been leveraged to a great extent. And when it first came out, I thought, well, it seemed like too small a number, but it did catalyze much larger investments by industry, along with, I think, the geopolitical situation catalyzed some of that as well. But anyway, I think it will remain the province of just a handful of companies, the very leading edge stuff. But I think capital seems to be there. Saudi Arabia just announced a $100 billion fund for semiconductors. And so I think the capital, even though it's immense, is there. And but the human capital is difficult. In the U.S., we haven't really been training manufacturing engineers or semiconductor people in the quantities that we need. So, like if you talk to TSMC, they'll probably tell you that one of the problems is getting enough people to work in their Arizona facility. And I'm sure that, Samsung and Intel will have similar issues, and that will be a gating factor. A significant part of the CHIPS Act money goes into actually training new people. So,
very interesting.
Fabs, though, have fewer and fewer operators running them, right? They almost have no humans inside. But the equipment, the logistics, and it still takes a lot of very qualified people to run a fab, a lot of highly qualified people.
Will those fabs that are being built in the U.S., will they be able to produce some of the top of the line Bitcoin ASICs, or will those be more of like just your typical fab? Like you said, there might be dozens of fabs all over the world, but there may be 3 or so that can produce top of the line ASICs.
No, I think these are all meant to be more or less leading edge. Maybe not leading edge in all cases, but leading edge. Yeah.
Very cool. Back to Bitcoin mining specifically, as the ASIC market changes and new efficiencies are made in different machines, do you think that there will always be these large mega Bitcoin mining farms, or will technology accelerate so fast that it might just be you need to buy the best ASIC you can and you plug it in anywhere relative to any energy price? You just got to plug it in first before everybody else, before hash rate and difficulty go up? Or do you still think that there's a place for these larger mines to always exist?
I think there will always be a place for the larger mines. I think that the benefits of scaling to a large mine, like for example, we don't really want any sites now that are not quite significant in size. The scale helps a lot. And, usually that's also a way of getting lower power prices. But, if you're buying effectively wholesale large quantities of power, as opposed to, I'm sure the power prices for homes, it's, in someone's home or office or thing like that is far, far higher than what these mining operations pay. Certainly what we pay it somewhat.
Yep. You brought up earlier artificial intelligence, GPUs. Obviously, NVIDIA is the stock in the traditional finance world that's been going crazy. Mm-hmm. How do you see AI and Bitcoin mining as far as GPUs and ASICs? How do you see those two industries kind of interacting?
Well, I mean, you might know that some of the Bitcoin mining companies, including ourselves, are going into hosting AI data centers. And our first one is in Singapore. And we think there is some significant synergy there. One thing they do rely on low energy prices. Running a large data center has some similarities between Bitcoin and AI, though there's a lot of differences also. And in our case, in particular, we're partnering with NVIDIA and making sure that we cater to people who need not just the GPUs, but also model support and software support and things like that. So the smaller and medium-sized businesses right now. But we are as good as anyone at finding low-cost energy and building out large facilities that leverage that. And I think for AI, that's going to become more and more the case, right? I think you're going to see the scale of the AI data centers measured in megawatts just explode. And I think Bitcoin mining companies like ours are well situated to to address that issue and to, provide value there.
Do you see like if there's for example, currently there's obviously a boom in AI and people are, buying all these GPUs to train their LLMs and whatnot. Does that massive demand take away from potential supply for building Bitcoin ASICs? Like, do they compete at all when it comes to building these chips, or is it still like Bitcoin still so small that it doesn't really compete against AI and other industries?
There's always some competition for factory time in these things, and especially if you're using the same node as the AI chips, then you will have to contend with that, and the allocation that you get, might be different than if you used a different node that didn't have as much demand. So that's something that people take into account.
Very interesting, Haris. This has been a pretty interesting conversation for me, at least. Where do you is there anything that I didn't bring up or didn't ask you that you think is worth mentioning to the audience about Bitcoin, about designing chips, about Bitcoin mining in general?
I don't know if your audience is interested in the halving that's coming up, but that's one thing that might be useful to cover.
Definitely. Yeah, feel free to talk about that.
So the Bitcoin protocol has this built-in cycle of roughly 4 years. And every 4 years, the amount of Bitcoin that get mined goes down by about 50%. Well, exactly 50%. And so we are about to hit another one of those times, and that's going to happen sometime this April. But right now, and for the past 4 years or so, every day we've mined about the global industry has mined exactly 900 Bitcoins a day, well, on average. And then starting in April, I think sort of the middle or late April, it will be 450 Bitcoin a day. Now, of course, there's also some Bitcoin that are given to miners for that are sort of paid out by people who want to make sure their transactions get included on the blockchain earlier or more aggressively. So its numbers are a little higher than what I just said, but that difference means that you have to be that much more efficient in your mining operation in order to survive and to thrive in this industry. So it's actually a good thing. I'm not sure if that's the reason that it was put in there. I'm pretty sure it's not, but it helps keep efficiency of the whole mining fleet at a high level, and it makes sure that you are constantly weeding out those mining rigs and companies that are not able to perform. And of course, the real reason that it's there is so that the total number of Bitcoins mined over time is finite. Keep reducing that number, and then eventually it goes to zero. And so then you have the 21 million finite number of Bitcoin. But then the side effect is that it continuously improves the efficiency of the global mining.
Yeah, it's going to be interesting to see how the halving goes, because I know historically, at least in I believe the 2016 halving and the 2020 halving, we saw like hash rate drop, especially during 2020, like fairly significantly, because those older inefficient miners were having to go offline. So, but also now the price is going up, so maybe it won't drop as much as we expect. But
exactly, I think it depends on what the price is when the halving happens, of how much hash rate you lose.
But I definitely agree. It's over time, if people can make money mining, buying the newer gen machines, the older machines are going to get pushed out and eventually turned off, or they're going to go scavenge for the free or cheap energy somewhere around the world.
Right.
But this is awesome. Thanks for taking the time to sit down with us.
Yeah, no, I really enjoyed it. Glad we had a chance to talk.
Yeah, this is great. Thank you.
Thank you.